comments about how energy can be obtained from the potential. So energy from phi, and you know who phi is by now. Okay, so what did we have? We had all this all these sets of equations for the work. Let's see which ones we actually need. We had an equation that was work for the point charge distribution. Let's see if I can muster it. Or we had the one for the field EPCD. Let me so we had this equation for the E of a point charge distribution. Maybe let's see if I can get it from here somewhere. Electrostatic fields, electrostatic point charges. Okay, so what did we have? We had this equation here. The electric field was just 1/4 epsilon 0, the sum of QI R over Q like that. And then we knew also that the force associated to this was just the measuring force, measuring charge times this. Then we talked about the work in order to build a collection of charges. Okay, and maybe that's what I'll try to get here. Energy in systems of point charges. We had this expression here for the total amount of work required to assemble a collection of point charges. You start with the first one, it costs you nothing. You bring in the second one, it costs you the value from the second, etc., etc. And if you look at this expression here on the right-hand side, what is this really? Well, it actually corresponds to the following equivalent expression. So let me just go write it and come back to this one if you want. So the work required to assemble a system of charges can be written in the following way. So here I imagine I've got again my my point charges, summation I from 1 up to n. And what do I have? I have the charge Qi times the potential which is felt by that charge at its position. Okay, so this equation here is exactly the same as this one here. I have simply identified, sum over j different than I of qj over r minus ij times 1/4 epsilon 0 as phi at the position ri where qi sits. Okay, it's the same thing. You can derive it from scratch if you want, but you have it here. Okay, so that's the way to get the total energy contained in the assemblage of these n point charges. Okay, so that's the one that that indeed I write as PCD. So the total energy of a point charge distribution in there, and then for continuous charge distribution, well, the equivalent of this is simply to change the discrete nature here to continuous nature, and what it becomes is just the integral over your volume. So let me indeed write it as d tau here of rho at r times the potential phi at r. Okay, here you might object that we're doing like fishy business with point charges and taking the limits and whatnot. Actually, it kind of works out because in the original thing here, we didn't have a kind of self-energy of the charges. Here, it seems like we do have a kind of self-energy of the charges, but actually it doesn't because the volume vanishes. Therefore, the actual energy content of that limiting volume also vanishes. So it's all okay. I think you were first. So in in the original point charge energy expression that we had here, we didn't count the energy of a single charge by itself. You know, so how much energy did it cost you to assemble this point charge Qi? So this one is out. Okay, and therefore the summation here over J is over J different than I, because there's none of that.
It seems like you write like a sum over both Q1 and on Q2 and also Q2 and Q1.
Which is why it's 1/8 pi instead of 1/4 pi, because in the second equality here we have symmetrized the second summation. Very good. Okay, that's why there's a half here, because you count it like twice. Okay, cool. So now, armed with this expression, we can just use the following things, and I'll be done in 2 minutes for your break. Don't worry. We're going to use the fact that rho from Gauss is just epsilon 0 times the divergence of E. That's from Gauss. Okay, so essentially what that gives us is that this thing here just becomes epsilon 0 over 2, the integral d tau of, you know, I can write it as div E like that times phi. Okay, so that's one thing. But now what I can do is I can use also the fact that E is equal to minus grad phi, and I can integrate by parts. To get the following thing. So what does that tell me? First of all, I just used the replacement here. So this becomes minus epsilon 0 over 2. Now the integral d tau of div of E sorry, no, I should div of grad phi or actually I probably want to do it the other way around. I'll do it let me just do it the other way around. So what I'm going to do is I'm going to restart from this one here. So epsilon 0 over 2, I've got the integral d tau, and now I'm going to write that I've got div of E times my phi here. But what I'll want to do is take a gradient of this. I will consider the gradient of div E times phi. Or actually, I will take, no, sorry. Let me just trying to simplify it, but I'm making it more complicated for you. Okay, so what I mean is that this thing here, I'm going to rewrite as the div of E phi. Okay, I apply the div. But then I can change that into just a minus am I confusing you here? So the div of E, I want to use the identity that this is going to be minus E dot grad phi. Okay, and then this is going to be for me the minus E, but then I can use the divergence theorem on this term here. So you see what I get, that I get a first term here by considering this one here, but now the minus grad phi is just E itself. So what this gives me is just from this term here, I just get epsilon 0 over 2. Now the integral d tau of E squared. Okay, and this E squared is really just E dotted into E. Okay? And then by using the divergence theorem on this term here, what I get is so if I have a certain volume here, then I will get an integral over the surface of this volume here of just the element here. So phi times E. And then there's a dot in here, right? So if you want, this is like a scale element. Okay, so this is just using this identity here, using the divergence theorem to transform the integral over the volume of the divergence of this object into the surface integral of this object dotted into the differential element. And then the second term here, I've just replaced minus grad phi by E. So I've just got that thing here. So this one here can be taken to 0 if the boundary goes to infinity, because at that place my fields, my potentials vanish, and therefore this whole thing would disappear. Okay, so this expression here, maybe I should just rewrite it cleanly. So the energy content of an electrostatic field is given by the integral over the volume where these fields live of E squared. Okay, and this is again superbly useful result. Okay, that we can use later on. Okay, we got there. You have a question?
So first of all, I have 2 questions. Does that mean that the impedance of nabla with phi that is equal to the gradient phi?
Sorry, what am I looking at?
So you're looking at the impedance of nabla with d phi under.
Yeah. So here this is a vector, right?
And phi is also.
Phi is a scalar. So you see, phi is a scalar.
But it's the potential.
It's the potential.
Potential is dependent.
The potential, it's a scalar field.
And then when you do the nabla operator input it with a scalar, that's the gradient.
Yeah. So if I write it in Cartesian representation here, let me go back to black. So here, what I mean is the derivative with respect to x of Ex times phi plus the derivative with respect to y of Ey times the same phi. Okay, phi also depends on x, y, and z. However, the expression that you have here, the dot here applies to the vector E if you want. It's just that each component of vector E is multiplied by the same scalar, which is phi.
Okay, and then how do you go from there to E squared?
So this one here.
Yeah, from that you go to not only that, but the whole thing. So right, because you said the infinite, so the divergence of that.
Yeah.
You go from that to E squared.
So here I'm doing just a little identity, right? So the identity I've used here is that if I look at the divergence of E phi, I get that this is the this is divergence of E times phi plus E dotted into the gradient of phi, like this. And therefore, what I have here which is this, is equal to this minus this.
Yeah, exactly. And then from that minus that, that's equal to E squared.
It's this one here. You see here, I have E
Yeah.
dotted into minus. This is like plus E dotted into minus grad phi. But minus grad phi is E. Therefore, this is E dotted into E.
That's E squared.
And E squared is just E dotted into E. That's the notation for this.
Exactly, because I still don't, that's E squared, I got that, but then before you said that the grade, so that's the gradient, or the I don't know English,
In het Nederlands kan ook, hè? Dus,
so the input, it's input, right, the dot.
here, yeah.
That one. So that input of E phi minus E squared is equal to E squared, or plus E squared.
No, it would be plus E squared.
Okay, so that plus E squared is E squared.
Yeah, so let's maybe label our objects. Let me call this one A. Let me call this one B. And let me call this one C. Okay, and here what we have is that A. No, sorry. So this is A. This is B. And this is C. Okay, so we're using that A is equal to B minus C in here. So A is equal to B minus C.
Yeah. So then how can A be equal to C?
Yeah, and essentially I have integral d tau of divergence of E. No, it's good that you're asking because it has to be seen. Okay, so and then by the by Gauss's theorem or the divergence theorem, this becomes the surface integral. So if this is over a certain volume, there's a certain surface bounding it, becomes the surface integral of this dotted into the vector itself, which is just E times phi.
Okay. Yeah.
And I can just take the phi out here because the dot only acts on this. And this is my expression here. Okay? So it's a kind of manipulation to get that thing. Okay, so what the message of that thing is that the energy content of an electrostatic field is the integral over all space of the intensity of that field, E squared. Okay, and we'll use that. Okay, but now I think it's high time for a break. And afterwards, we'll get back to our Laplace consideration.